In this video, we're going to delve into the dangerous areas of shift operators. So you've received warnings about doing shift operators with negative numbers and warnings about shifting equal to or more than the number of bits that you have. So we're going to explore what happens if you ignore those warnings, and maybe that will give us an understanding for why those warnings are there. I've written a simple test program that takes a char b, which is a signed 8-bit number. We're setting that equal to 64. Now, 64 will have the bit right before the signed bit set. Okay? So when we shift over by 1, b is going to effectively get multiplied by 2. So that will result in 128. Now that's an overflow because an assigned 8-bit number goes from negative 128 to positive 127. So we have an overflow condition, and we're shifting to the right, dividing by 4. So let's see what we get. We run this program, negative 32. All right, it's kind of what we expected, right? Shifting to the left, it's going to make a negative 128. And then when we shift to the right again by 2, we're dividing by 4, so that's going to give us a negative 32. So it's what we expected. Now, what if we simplify this a bit? So we'll take these 2 lines and we'll make them into 1. So we don't change anything at all. Not changing the logic. We just make 2 lines into 1. So let's run it. See what we get. 32. Not negative anymore. What is going on? So it turns out in this first parentheses here, when we shift b, b gets promoted to an integer, a 32-bit integer. So when we shift 64 over by 1, we multiply by 2, which gives us 128. This is not an overflow. We're not shifting into the sign bit because we just shifted into the 8th bit, not the 32nd bit. So when we divide by 4, it's still going to be positive. Okay, so hopefully that gives you an idea of why signed numbers and shifts are dangerous. Let's look a little deeper. I have another test program, this shift test. At the top, you'll see there's a function for printing binary numbers, and here I'm setting n equal to a binary number. I'm using the 0b syntax, which is a GNU extension. So n has the bit right before the sign bit set, and b has the bit right before the sign bit set for 8-bit numbers. Okay, we're printing out n and b, and then we're shifting to the left 1 and then shifting back to the right by 2. Now there's another section of code that we're going to experiment with later, so I'm commenting that out. So let's run this. Okay, and again, we see that we get negative 32, right? And here we get a negative number for the integer as well, because with the 32-bit number, when we shift left 1, we do go into the sign bit. So that's what's going on there. Now let's uncomment this this other experiment where we're going to take that 32-bit number and we're going to shift it. You'll notice that the 32-bit number here has multiple bit set, not just the top bit. But we're going to shift it up to 32 bits, which is 32 is the number of bits, so we're not supposed to do the 32. So the compiler would warn us if we hard-coded it, but we're using a variable, so the compiler can't really tell. So let's see what happens here as we're shifting over. Shifting by 0 does nothing, right? And then we start shifting 1, 2, and the bits shift over just like we expect. But look at 32. When we shift by 32, we actually get back the original number. What's going on there? Turns out that's shifting by equal to or more than the number of bits gives us undefined behavior. On an Intel, this is what happens. We get the original number back. So, I don't know. Maybe that's cool. You might look at this and say, wow, I could do something with this. This would be cool. I'll impress my coworkers by taking advantage of this fact. Well, before we do that, we should check it out on other architectures. So I have a Raspberry Pi, which runs an ARM processor. Let's look at the same test on a Raspberry Pi. Okay. Again, we will change it to shift over to 32 bits. So we compile it. We run it. Now look. Interesting. Again, the bits shift over as we expect. But when we get to 32, it goes to 0. It's kind of cool. That's what we were expecting. That's what we were expecting, which is kind of nice. So is ARM doing it right? Well, we should shift more than 32 just to make sure. So let's shift over by something much larger. Let's shift up to 256. All right. So again, we compile and run it, and look at that. Yeah, if we shift more than equal to or more than 32 bits, all the bits shift off, and we get 0. That's awesome. So now we might think, okay, ARM is doing it right. There's no weird behavior here. Well, let's make sure. Let's shift one more than 256. Well, let's shift 256 and see what happens. Just to make sure. Look at that. If we shift 256 bits, we get the original number back. What does this tell us? Well, I really hope that it tells you don't shift more than, or don't shift equal to or more than the number of bits you have. Undefined behavior, it's works differently on different machines, which is why we call it undefined behavior. Don't do it. And be very careful with shifting with signed numbers because the results there are also unexpected. Okay, so these bitwise operators are very powerful. You'll use them a lot. Just be careful out there.